Well, it's time. Welcome back, folks, and happy midterm week. We're pretty much at the midpoint of the entire semester at this point. And as far as midterms goes, there's no special project or anything like that. Like I think I mentioned before, all we're going to do on midterm week is on Friday of this week, once I get completely caught up with grading all the quizzes, pulling the homework assignments that are past the due date in my lab, I'll update your course score in the grades here in Canvas, and that gets converted into a letter grade, becoming your midterm grade. Well, for where we're at so far, we're on example 3. We started it, but we just didn't get to the step of putting the information into the calculator just yet. So we have a few more examples to go through in Unit 4D, and then that'll be the entirety of Chapter 4. We're going to move on next to Chapter 5, Statistical Reasoning. Well, any questions at all, folks, to start us out today? Okay, let's jump in. So we're on the final unit for Chapter 4. I think this is a pretty fun chapter, so it's kind of sad to see it go, but we're on to next newer, better things in Chapter 5. Not necessarily better, but definitely newer. In this chapter, there's lots of different skills that we're practicing all at once, in this unit rather. We had to determine what are the variables in the context, what's the principal, what's the term, what's the APR, and so on. The second big skill was we had to use the formula that was on the Canvas page. Here it is on the red dot, or down below rather. Fill in the information to that formula. And then the third skill, sometimes the trickiest thing about this whole thing is to take that information, plug it into a calculator, and get a value out. So let's start off a bit slower on this example, just as a warm-up. If you have a calculator nearby, that'll be really helpful. We'll take this slowly, looking at both the TI-30 X2S and the infamous TI-30XA to try to get this information exactly right. So first, plugging it into this kind of calculator, it's going to look about like this. You would want to take this entire set of information, write it down as one line altogether, and that would say the payment is really 475,000, open a parenthesis, 0.075, divide by 12, then divide, open another parenthesis. There's no brackets in either calculator, so we'll just have stacked parentheses. 1 minus, another parenthesis, 1 plus, 0.075, divide by 12 again. Here, sometimes it's a good idea to just do one step in the middle, so we're not putting in a whole bunch of stuff. One step in the middle, even before putting the whole thing in the calculator, is to take 12 times 40. So we are going to use an exponent of negative 480. So raise all this to the power of negative 480, then close that final parenthesis that matched up with this one. So that's what it looks like in this calculator here. The keys you would have to be using are going to be parentheses key for each set of parentheses we opened. For the exponent, we'll be using this up arrow, excuse me. And for the one negative sign, this one, we have to use the negative sign down there. The subtract key won't work if we're trying to just put in negative 480. So this is what it looks like in the calculator again, except you have to scroll left and right to see the whole thing. Let's see what we get getting a value out, and let me know if you're having any trouble getting that value. So for Desmos, looks pretty close to what we put down on paper. I have 0.075 divided by 12. Oh, that's a weird set of parentheses. Let me Control Z that out. So that's the entire numerator so far. Then for the denominator, these outer parentheses aren't strictly required, but they are if you're putting it in the calculator. So that's why I offer parenthesis brackets right here. 1 minus 1 plus 0.075 divided by 12 to power negative 480. So I'm getting a payment, this is a lot, of $3,125.84. Let's put this on paper. $3,125 84 cents. How's it look to folks so far? Anyone getting any different values, or does that look all right at the moment? Okay, so this is just one calculator that you might have. The other calculator could be this one. So let's practice this one more time, working it out in this calculator. And thanks goes out to the student from last class on Thursday mentioning you can in fact put this in a slightly more reasonable way. You take advantage of these parentheses right here. So if you use these parentheses, we can actually put this in the calculator in a decently similar way that you might use the other calculator on. We'll have to use those parentheses. This is the exponent key in this particular calculator. To change to a negative sign, we'll have to use that symbol down there. And then the standard other operations, multiplication, division, equality, and to get the value finally. So to practice this calculator, let's take a look into this just as a set of pieces. I have a numerator of 2,968 being divided by this denominator. If we see these values come up, it's going to tell us we're on the right track with this calculator. And here's how it goes. You want to always be really slow and careful, very methodical with this calculator. Oftentimes, if you miss something up and don't quite see it, you just have to start all over. So start off by putting in the 475,000. Then we can't put in a parentheses just yet. You have to next hit the multiplication symbol, then hit the open parenthesis, and your calculator display should say 0 at this point. Now I'll put in the 0.075, immediately hit the division key, punch in 12, and next we just want to close the parenthesis. I've got a 0.00625, which looks concerning, doesn't seem like we have the numerator. But the next thing we're going to click is the division key to match up with this fraction bar here. So hit divide, and you'll notice your calculator should read out this value right at this step before we've pressed anything beyond the division key. So if you see the numerator pop out, then you're on the right track. Then it gets trickier, but we can navigate through this. We have to open a parenthesis to start, so click on that key. Then type 1 minus this minus key right here. Then we have to open another parenthesis, so hit the open parenthesis key again. We'll go inside 1, then plus, type in the 0.075, hit division key for this stage, 12. Now we'll close the parenthesis. I'm looking at 1.00625 at that stage. We need to put in the exponent at the very next step, so that's going to be the y power x button. So hit that, then type directly 480. Don't worry about the negative sign just yet. Once 480 is displayed on your screen, to get that negative sign, we hit this key right here. And all we should have to do is close the parenthesis. Once the parenthesis is closed, this number should be on your display, 0.9497 and a little bit more. Okay, it looks like we've got that so far. We've already told it to divide, so the calculator has stored this number and this number. We just have to hit the overall equality key, cross our fingers, and hope to get this. Yeah, on my calculator, rounding to the nearest cent, I have the same value. It's definitely tricky, and thanks again for the student to pointing out it's not as bad as I made it out to be when we looked at this on Thursday. If you use these parentheses keys, you can type this in an ordinary flow left to right, just like in the prior calculator. Slightly more tricky, especially since you can't scroll left and right to see any part of the computation. But with practice, I practiced this a bunch before class, it's not so bad. But we've got the values out. Any questions at all, folks, getting those numbers? Okay, well, we're through the calculator side. If you're having any trouble doing this in MyLab, don't hesitate to reach out. You could take a screenshot of your MyLab homework set. You can click the Ask My Instructor button in MyLab as well, or just suggest the problem at the start of class. I'll be very happy to help out with it. Usually, I find that for these kind of problems in MyLab, oftentimes people know exactly how to do it. It's just something along the lines of maybe a rounding error or something like that going on. The major thing that we're also practicing at the same time is, for the sake of MyLab, we didn't round at all until we rounded to the nearest cent at the very end. So finally, we've got now, putting all this together, a pretty big payment, $3,125.84. In this particular context, we're supposing you work for a bank and you're just giving people a ballpark idea of what numbers might look like to determine if they can afford a mortgage payment. There was research done to find that the median mortgage in Idaho is 475,000. So we made that our principal. And maybe they looked at the 30-year mortgage already and they decided that's too costly. Don't quite have it there. So they looked into extending it to a 40-year mortgage. These really do exist. It was kind of surprising to learn about that. At an APR 7.5%, we find that that's the payment. They're going to try to pay down what's almost $500,000. But the payment, monthly payment over a term of 40 years is absolutely not the whole story to this. When you're doing this kind of loan, by law, if it's an auto loan or a home mortgage, the bank is required to tell you certain things. They'll tell you how much are you actually paying over the 40 years, and what percent is going to go towards the principal, what percent is going to go towards the interest. So this is just as important as finding out the payment, but really it's not too bad once we get through that number right there. So here's what we would do next for the Part B portion of this. Take this, $3,125.84. This is a payment per month. Then multiply by 12 months per the year. Multiply that by the term length, which is 40 years. And here's what we're going to have them paying out. So $3,125.84 times 12 times 40 years, it comes out as $1.5 million. The $403.20 are important, but it seems kind of small, right, compared to that total amount. So putting that down on paper, they are paying $1,500,403.20. Once they get to that last payment, that's how much they've given to the bank. And we can kind of see what this is going to come out as. If the principal was $475, close to $500,000, and they've paid this much in total, it looks like they've really only paid about a third of this towards the principal, 2/3 towards just purely interest. Even though the interest rate was low, a very long term like this, and 30 years is already a long term, but this means an overwhelming amount was paid towards interest. Well, that's going to be our last two computations, getting a 2% down. Any questions so far? Okay, so now let's look into, of the total amount paid, what percent is paid towards principal. So I'll just say briefly, percent paid towards principal is going to be, when it says of the total amount paid, that takes this value right here, throws it into the denominator. So 1,500,403. And let's not forget the 20 cents, every cent matters. That's going to divide into 475,000 even. Then last go times 100%. and we'll get a value out. So back in this calculator, 475,000,150,00403.20 times 100. All the percents here in this section are rounded to just the nearest tenth of a percent point. So we'll call this 31.7%. So only 31.7% is paid towards principal, less than a third. And so now that gives us immediately percent paid towards interest. Here, we don't have to work as hard on the first, like we did on the first one, because there's only two sources this money is going towards. Either it's the principal or the interest. The total is 100%, so we can just take 100% minus the prior answer, 31.7%. And that's the amount towards just interest. So in the calculator, go 100 minus 31.7, 68.3% towards just interest on this. So for the privilege of paying back almost $500,000 over the course of 40 years, almost 70% of your payments, here they are, is going towards that, just purely interest, right in the bank's pocket. Well, we did it, folks. That's the conclusion on this problem right here. Some of these numbers can be kind of surprising and shocking. For example, on the last problem, when we were looking into the 15-year mortgage, the interest rate was a little bit better, but that's kind of reflected on the shorter term, giving a better rate. Here, it was almost a complete flip of what we have on the prior problem. Almost 70% went towards the principal on this one for a 15-year term. Of course, the value is a lot less. And when we go to this value over 40 years, now at a higher rate, which is typical, extending the loan term for so long, it's almost completely opposite. Now just about 30% towards principal in this case. Well, we'll look into just a couple more scenarios. I think the next one's going to be a car payment and then a credit card payment. But more just practice getting used to this formula, conveying in the information, and working on the calculator are the major skills. Any last questions at all before we try out the next? Okay, 2 problems to go, and we'll be done with this chapter. I noticed a typo when I was reading this problem to start out today. This was supposed to say buyers, so I had to pluralize it. That's for the change there in red. And here's what the scenario looks like. It says, suppose you are considering an auto loan of, let's just say 50,000 even. Probably they're going to bump up that loan a little bit higher. Well, let's suppose it comes out to $50,000 to purchase a new BMW 330i, beautiful car. So I can see the temptation. It's going to be at a fixed APR of 7.199%. That's kind of annoying, but this is kind of reality sometimes when you're getting interest rates from banks. It's kind of like buying something that's $1.99 at a grocery store to make it seem like it's not the full impact of $2. They're just trying to do a little psychology on us. And same with interest rates. This is going to be a car loan. So now at essentially 7.2%, but we'll use a 0.199 in the computations for a term of 84 months. And that's a pretty surprisingly long auto loan. I found out that these are rapidly growing, and roughly 20% of buyers of brand new cars are going for the 84 months. So here's the entire situation. We want to find out if we're getting into this loan for 84 months, what is the monthly auto loan payment? And we'll round in the final cent once we get to the last part. We won't round in the middle, rather. Well, this all comes together in the same kind of way. First thing we want to determine is what is the principal amount for the loan? That's going to be the $50,000 we'll get funded by the bank that will owe. So $50,000 there. Next thing we'd want to know is what is the APR? We're told that there's a fixed APR of 7.199 altogether. So APR, now written as a decimal, is going to be a 0.07199. As opposed to the last section, when we look into our formulas, there's an n value, but n is always going to be 12 for the 12 months, just to make this kind of a realistic problem. It'd be weird to have a car payment you pay, like, say, quarterly. That'd be really weird, or more than once a month. Next thing we want to know is the value for y. But already that's kind of tricky. When we go to plug this into the formula, here it is for easy reference. We can't put the 84 in for y. They gave us months, so we need to do a unit conversion in the middle on this one. This is, again, pretty typical for auto loans. For some reason, maybe they just feel like it's easier to get you into a 84-month term loan rather than, say, the number of years. The number of years might feel not as nice. So we'll say y, first do a conversion in the middle, is going to be 84 months. Then multiply that by 12 months for each year. And now we'll have the term length after doing that conversion. So let's take 84 divided by 12. You might have already done that. This one is a 7-year loan. And even longer terms for auto loans are starting to come out. But this one is the rapidly growing one, the 7-year loan. I think when people see 7 years as a loan, the big question they're going to have is, will the car even run once we get to the 7-year mark? That's kind of iffy for some car models. But nonetheless, they'll still give you the loan. And if it breaks down, the engine blows out on year 2, you're still on the hook for the entire loan. Well, let's find out the payment for this. The interest rate is not too bad. The principal is kind of large, but we're going for 7 years, so it sounds like the payments are going to be somewhat low. We'll put this all together by saying payment is 50,000. Take now one, or excuse me, not 1 plus, but rather the APR, 0.07199. Divide that by 12. Then in the denominator, go 1 minus, 1 plus. Then just start copying all the way to this part right here by the red dot, 0.07199. Then divide by 12. Raise it to the power of, in place of n, once again, put in 12. But we're multiplying that by 7. And we already know that this is going to come out as an 84, so that number of months is already reflected here as an 84. Now, final thing to do, the careful step is throw this all into the calculator and we'll see what we get. Work this out on Desmos and let me know if you're getting something different. I'm happy to break it down for the TI-30XA or the TI-30X2S. Okay, so I've got, after throwing into this calculator here, $759 and 51 cents after rounding to the nearest cent. How does that look to everyone so far? Are folks getting to about that number? Okay, again, if you can get right here rounded to 51 cents, then you're in great shape for MyLab. As far as grading these on exams, I'm not going to be super critical on the exams. So if you're within, say, a relative error of about 2 or 3%, I won't be too worried. You'll probably get full credit on that. The number is way off. You might lose a point, but I'm giving a full point for just saying what the quantities are. Another 3 points, I'll add a 5 for putting it together correctly in the formula as you see here on paper. And then the final point is to get the exact number out. So we're really going to emphasize the calculator in my lab, but for the exam, I'm looking into the concepts most of all, less about the particular computation. But once we get here, we can now determine how much is going to be paid over the 7-year term on this auto loan. So it's a pretty humongous payment when you think about it. Those used to be mortgage payments or around that magnitude there. But this is now for just a single car, $759. 51 cents per month is the payment. We'll multiply by 12 months per the year. That way we can now multiply by the 7 years. I guess we could have multiplied by 84 months. That might have been a little bit faster, but keeping this parallel to what we did before and focusing on the term of actual 7 years, let's multiply by 7 years here. And here's what you'll get. To completely own this car and get the title back from the bank, we'll have to take, not that number, rather, this amount, 759.51, multiply it by 12 months, multiply it by 7 years, and we'll be paying $63,798.84. Which makes it easy to see how much extra in excess we're paying on interest. Interest is then $13,798.84. And that's not fantastic, but in view of the last problem we just did, where the principal of almost a $500,000 turned into a total payment of 1.5 million and a little bit more, this doesn't feel as bad. But if we could have changed the term to something smaller, or maybe just buy a cheaper car, or wait until the economy cools off a little bit for interest rates, APRs are starting to come down bit by bit currently, this might have been a better picture altogether. So if you still want to buy this car, we're imagining buying the BMW 330i, the bank is also going to have to show you, in addition to this number, percent of that's going to be paid towards purely the principal and paid for interest as well. So we come back to these numbers here. Same kind of stuff that we did on all the other examples, but really the payment amount is not the whole story until we get the total amount and look at these two percentages. So let's organize like before, and say, just briefly, total paid towards principal is going to be, take the total value, $63,798.84. And towards the principal, we're only paying $50,000 in total. Rest goes to interest. Hit times 100 to convert it to a percentage, and here's what we'll get. 50,000 divided by 63,798.84 times 100. And this is a much better picture than the home mortgage problem we just ended on. It would be nice to see this a little bit higher, but 78.4%. Sure, it feels better than about 30%, like in the last problem, towards principal. Well, once we have that, we can do the standard thing, 100% minus that number to get the amount paid for interest. But any questions at all, folks, getting to that value there? Okay, let's look at the interest side. Total paid towards interest next. we'll take 100% minus 78.4%. And it comes out to 21.6% altogether. Well, we did, folks. This is the information you would see getting into the car. But sneaky thing about car loans is that might be the sticker price, and then they're going to try to sell you all of the extras. They might want to do some kind of sealing under the car. They might try to get you maybe gap insurance. They might try to get you maybe an extended warranty beyond the manufacturer's warranty. They can throw on loads and loads of extras on that and bump up the principal loan to an extremely high amount. And then the whole picture changes after that. But any questions at all, folks, getting through the auto loan payment? Okay, well, we're nearly done with this section. There's been quite a few different kinds of weird problems going on in this section. First one was a personal business loan. We looked into some mortgages, now a car loan. And the last one will be for a credit card loan. Revolving line of credit on a credit card. You can't really do a section like this without talking about credit cards. And so here's a scenario on this one. And it's a pretty reasonable scenario as well. It says, suppose you're starting out a new job as a professional auto mechanic. You've completed all of the technical school, got all the certifications, and maybe you're about to be signed up by, who knows, maybe Jiffy Lube or something like that. Maybe not Jiffy Lube, maybe something a little bit more than that for the auto work. And the one thing I learned that was kind of surprising is every auto mechanic that works for an auto body has to buy their own tools. And these aren't cheap. If you want to get, say, pretty decent quality tools, I think this number might be low, but let's just go with it. It's not unreasonable to imagine that you just got out of your auto school and now you have to spend $8,000 purchasing quality tools. Maybe you already had those when you were in the tech school, but either way, let's say you spent $8,000 just for the privilege to work this job. It's like some kind of extreme extra tax for this one industry. And you may not have had that money up front because you've had to pay for school already, for example. And so we've purchased $8,000, putting them on a credit card that has 29% fixed APR. That's kind of high. Again, APRs are coming down a little bit, but let's keep it at 29%. We're told the total balance on this card is now $11,000. I should have put a comma there just for readability. $11,831.78. So the card already had a balance. It wasn't extreme, but now it is. That's quite of a balance for a credit card. So this person may be feeling guilty and wanting to get that paid down, hides the credit card out of sight on the bottom of a drawer that is almost never open, and they hope to have it fully paid off in 5 years. That's their goal. So we're going to make the assumption that no purchases are ever made with this card over the 5-year period. Maybe they did get hard times if they opened a new card, but on this one, no additional purchases are ever made. So like before, we want to use our formulas. Here they are. To find the monthly credit card payment in this context. And context is really a lot on this one, but it's pretty realistic. So we have to do the careful work of finding all the values that corresponds to this formula. Taking the same approach as we did on all the other problems, we want to first spot the principal. And the context like this can get kind of messy. If we use the 8,000, we're not on the right track. We're trying to take down the total balance, which was 11,000. So we have to use this as the principal. So $11,831.78. So we've got that part down. Next thing we need is the APR, the annual percentage rate. It's 29% fixed APR. And so we'll write this in as APR equals 0.29, our highest interest rate yet on this entire section. Now it says next, credit card is hidden away, and the hope of hopes is that this card is fully paid off in 5 years. That's going to be the term, but let's also put in the end value is 12 for monthly payments and will be 12 months. And they directly told us the term is going to be 12 years. Okay, once we get all those values out of the context, then it turns into a math problem. We'll just throw it into the formula and see what we get. Any questions at all, folks, with the context itself? Oh, good question on that. And when I practiced this problem for the first time, I actually wrote it in as a 0.029 as well. But because it's a percent, what we would do is, converting it to a decimal, go 29. Percent symbol really literally can be thought of as per 100, and it gives us the 0.29 altogether. So we're doing a decimal shift from the 9 value just to the front of the 2 like that. But actually, that's one thing that's really tricky about this problem. When I was practicing it right before class, oh, thank you. Yeah, that should have been 5 years. Thanks for spotting that. When I practiced this before class, I made that same mistake and put it in as a 0.029 instead. And thanks for Zach for spotting that. That should be 5 years. I'm not sure. Maybe I was looking at the 12 when I put that down. Other questions at the moment? Okay, thanks for the help with the questions there and getting that term length right. So now putting this together, here's what it's going to look like. Payment equals, take principal, 11,831.78 cents. Multiply it by APR 0.29. Divide by 12 monthly payments, so division by 12 there. Echo says, I try to remember the decimal goes to the left twice. Yeah, that's a good way to think about it as well. So starting at this 9, it would just go left, land right there, the 2 positions. I think what threw me off as well is the interest rate is so high, this one actually just feels way different than the rest of the problems. Notice that in essentially every single problem we did, except maybe example 1, aside from example 1, essentially every problem we did had a 0 there and then the rest of the numbers. So that's what happened in example 2. Same with example 3. And same with example 4. And so when we return to an example like this one, where the rate got really high, it just doesn't feel like it's right anymore. It feels like it broke the pattern of every other problem we did. But that's only because the rate's gigantic this time. So having a way to do it, to either division by 100 or shifting the decimal place 2 spots left, like Echo suggested, is a good way to just kind of make sure we're not falling into the patterns of how the other problems went as well.
Sorry, I had a question. Is the principal the 8,000 amount or is it the 11,800?
It's going to be the 11,000. And again, that's another thing that's tricky on this one. There's an 8,000 charge, but this problem is more about the total balance being paid off entirely. So after 8,000 was charged, the total balance jumped to 11,000. So maybe they had some other things already charged on that account. And now they want to pay off the entire card, get it fully paid off. So that's the entire balance now, not just the 8,000 in 5 years. Does that make sense with that question there?
Yeah, thank you.
Yeah, you bet. And honestly, that's what makes this last example 5 really tricky. It's kind of a pretty decent real life kind of scenario that's happened. And it's hard to really tell exactly how we're meant to be analyzing this problem, whether we're talking about paying off the 8,000 or the total balance. It's kind of hidden in the context. We have to read through it a couple times to see what is the objective on all of this. But if I wrote this in as an exam problem and you interpret it differently as spending the 8,000 and paying off just the 8,000, I would have given full credit for that interpretation as well, since that's a reasonable assumption to make based on the context. For MyLab problem, though, they have one interpretation and only one. If this was the MyLab problem, they would have been going for the 11,000 altogether. Other questions at the moment? Thanks for the questions so far. Okay, now that we've got that numerator in, we convert down to the denominator, plug in those values. A parenthesis, let's keep it a bracket maybe. Bracket 1 minus, a parenthesis 1 plus, then APR again, 0.29. Divide by the 12 months for the 12 monthly payments. And let's do a calculator operation for the n times y, only because that's a good step to save in putting this into the calculator. It's big and complicated enough. We're taking 5 years of payments times 12 monthly payments. So that n times y is going to come out as a negative 60 altogether. So negative n times y came out as negative 12 times 5 for a negative 60 is what we got right there. With all that plugged in, we're ready for a payment. Okay, once again, try this out on your calculator. I'll put it in Desmos kind of slowly, and let me know if you have any questions on getting the value. We'll definitely double check the calculators as necessary so we can all get it right. Awesome. Echoes has 375.56. Let me see if I can get to that number as well. Okay, looks like our numbers agree. I got to 375 and 56 cents as well. So payment comes out as 375.56. Any questions at all, folks, on getting that number here for the payment? Okay, it's a heck of a payment, but again, it's a large balance. The APR is pretty gigantic, the largest one we've seen all notes. And for certain years when the prime lending interest rates were high, that was not an unusual interest rate on credit cards. So this makes this problem pretty realistic, unfortunately. The payment's pretty high. Now we'll see with an aggressive payoff in 5 years of a large balance at a pretty high payment. This is again like a car payment or half a car payment based on the last example. We'll see just how much is going to be paid in those 5 years on this card, and then do the analysis of what percent it was paid towards principal, what percent towards interest. So for this step here, just for the sake of the notes, let's write this down one more time. We're going to take 375.56 per month, multiply by the 12 monthly payments per year, then multiply it by, the goal was to pay off in 5 years, so that implies a term length of 5 years. But in all these problems, it's been pretty much the same analysis. Take the payment times 12 times whatever the y value for term length came out as. So in this problem, it's 375.56 times 12 times 5. And that's a lot. I mean, it's not like 1.5 million in the mortgage problem, but that was an entire mortgage. For a credit card that got up to a balance of just under 12,000, we're paying in total, if we stick to this 5-year plan, 22,533 and 60 cents. And you can easily imagine that when you look at these, say, credit card statements, the minimum payment is probably pretty high, but I bet you it's below this for a reasonable situation. If you only made the minimum payment, that minimum payment changes over time as well. it will tell you on a credit card statement, I think this is also required by law, how much you would make if you only made the minimum payment every time you saw the minimum payment. And it would be even higher than this by a lot. But this value is still pretty rough. But this is a professional getting started. So probably they're going to have months where they might be able to pay more than the 375.56. This is their minimum payment for a stated goal of 5 years. So if they really stick to that, didn't deviate one bit, we'll analyze the percent paid towards principal and percent paid towards interest. We can probably already kind of see it. It looks like towards principal, we're in the range of around 50%, comparing that total to that principal. So let's get this on paper. We can now say the percent. I think I phrased it slightly different as the total, but wrote it as a percent. I'll say the percent of the total, meaning the total amount by the red dot, towards principal is going to come out as, take the total, 22,553.60. That's dividing into the original principal amount, the amount we had after charging 8,000 for the professional tools, $11,831.78. Then times 100%. And here's the figure we're going to get. 11,831.78 divided by 22,553.60 times 100. So to the nearest tenth of a percent, it's 52.5%. And again, it's pretty weird for professional mechanics that this is a pretty nasty tax that they just have to face whenever anyone new is getting into this industry, buying the new tools. And on a credit card, this was a huge punishment. Only half of this payment over the 5 years, a little bit more, went towards just the original balance of the total amount, 11,800. So now we know just under 50% went towards interest. Let's just put it down on paper to finalize it. The percent of the total towards interest will be 100% minus the 52.5%. This comes out as 47.5%. Well, we did it, folks. That's the end of the entire chapter 4 notes on payments for this unit. Any questions at all getting to these last numbers?
I have a question, and it's just because of the way I read this problem, and I want to make sure that I understand, so on the exams I answer it appropriately. When I first looked at this and it said that he spent the 8,000 purchasing his tools, and then I looked at the 11,000, it looked to me like that was just the interest that had been accruing over, however long he had it before he decided to pay it off. And so then when I was looking at the total amount paid towards interest, my thought was to use the 8,000 instead of the 11,000 as the principal, because that's what was originally purchased, and wasn't interest. So I just want to clarify moving forward, like for quizzes, just to only take what we actually use for the principal and not really look at, don't make assumptions. Does that make sense?
Exactly. It does. And yeah, there's really two kinds of ways you could have gone on this. So if you went, say, 8,000 on this one, you would have had to put 8,000 here. It would change the payment amount, so there'd be a change there. Then there'd be a change on the total amount. And then you just reuse the 8,000 here, and you'd be on the right track. And again, this one was really tough to see exactly what is it we're doing on this one because the context mentioned multiple values at the same time. So if you kept it consistent going, say, this way, I would have given that full credit on a quiz or an exam scenario as well.
Okay,
But
good
yeah,
to know.
awesome. Thanks for asking about that. And yeah, it gets kind of confusing, just the wording, like you were mentioning, coming down here, paid towards interest, and the principal, when we're thinking of these original values, the only way we might have lost a point is if we went back to the 8,000, used it here, but not here. So in other words, if you're consistent with those values, I'll just say you interpret it differently for the problem on a quiz or an exam setting, and I would have given that full credit. But if we swapped up the values from one end or another, that's when we might have lost credit, for example. Well, other questions or comments on this one? Okay, about that context, this is one of the things that gets really tough in statistics, for example. Statistics has lots of context. Sometimes it's really hard to tell what is being measured, what is the population, what is the sample. So part of the reason this one kind of got a little bit weird with multiple values, we had to think really hard of what was the objective, really, total balance versus the 8,000 charge, was it's also meant to segue into what we're doing in statistics. So that's what we're going to take a look into. We'll maybe do one or two problems in our next section notes, starting in Unit 5A, Fundamentals of Statistics. We're only going to cover one chapter of statistics. We're not going to try to get too bogged down. There's an entire course called Statistical Reasoning that goes for the entire 16 weeks. So we're just looking at an overview of some major ideas, but really thinking about the context right here as being really the major skill we're going to practice when we turn over to our next unit on statistics. So let's open it up, see what it looks like. So we have a big wall of definitions that we're going to break down carefully, methodically, apply them to examples. As we go through these examples, let me see if there's one in particular. Sometimes the context looks like this, just a wall of text, things that we have to kind of interpret about the problem, pull out, determine what's the population, what's the sample, what is even being done. And these are pretty realistic contexts. It's meant to be, again, similar to what we did in example 5, the hard work of finding these values, the working it through the problem, by digging it out of the context, and sometimes we really have to dig hard to figure out what is the problem really even about, is the carryover skill to the next section, much like we're seeing in these long contexts in the end of the problem. So with that in mind, let's go to the very top and start breaking this down. Yeah, I wish I kind of partitioned this a little bit differently. Let me put in a couple breaks here, just to break up the thoughts. Our author starts with just a definition of statistics, and he's fancy in the sense that there's really two definitions he can give. First, you can think of statistics as a science of collecting data. How you collect it, random sampling is one part of it. Organizing the data, how you display it, what graphics you're going to use, what statistics are you going to use to represent the data, and interpreting the data, inferring something about the population, which we'll call inferential statistics, is all just one big subject, much like biology is a subject or mathematics is a subject. But when you say the word statistics and use it differently, statistics are the data, number or other pieces of information that summarize something, like you might say a sample average or a sample standard deviation. You're talking about statistics as a number versus talking about statistics as an entire science on the first definition. That's important because we have a definition of sample statistics, and we have a chapter called statistical reasoning, really thinking the first definition there when we say statistical reasoning. The second definition when we say sample statistics. So that's the first breakdown. And then there's another really big break right here. I should have put it on the notes originally if I thought about it. Here's where we're starting to think about the context really very hard, just like in the last example. There's a big dichotomy in statistics. It goes population versus sample. So we think of the population as the entire collection of, or the complete set of, people, objects, maybe animals or otherwise, that we are trying to study. So one population could be, for example, all ISU students. It's a very large population in the tens of thousands. And the sample to study a population is a subset of the population from which raw data are actually obtained, things like the sample statistics. So just for a really fast example to think about these two definitions, let's put down a population and a sample. Any questions first with just the definitions themselves?
So what you're saying is like if we're doing a study of ISU students who drink water, but we decide to only poll 50 students, then 50 students would be the sample size of the thousands of students that go to ISU?
Yeah, exactly. That's exactly what we're saying here. Let's put that down on paper. Let's say population. Let's say, for an example, I guess I can spell the word out. Example, all ISU students. And here's where statistical studies get really quite hard. You have to be very precise of what you mean by all ISU students. You have to say what your population is exactly. We can possibly be more precise if we say all ISU students registered for spring 2026. So the spring 2026 semester. And even that, you might have some issues with that. Say, maybe what about people who just do the late 8 weeks course and they're not yet registered, but they eventually become registered? Are they in our population? You can come up with a lot of technical issues with just trying to say a simple population like all ISU students. But let's cap it off right there. All ISU students registered for spring 2026 is our population. And then, like you said, a sample. Well, why would we want a sample? It's because this population is very, very large. It's hard to work with. And depending on what we're trying to measure, we might not be able to access every single ISU student to come up with a measurement on every single person. So instead, if we're trying to understand a population and we have some research question, like say amount of glasses or amount of cups for a specific measurement, or maybe just say the number of ounces the student drinks per day, we are not going to try to pull everybody in ISU. We can go for a small sample. So a sample might be 50 students, let's say 50 ISU students registered for spring 2026. So we're going to go for a reasonable sample size. This is still probably a good amount of work. It'll cost money to get a random representative sample of 50 students that really represents all ISU students. And again, maybe the question is, how many ounces of water they drink per day? We can compute that for every 50 students, take the average or the mean, we'll call it later, and that's going to be a sample statistic. So let's say here, just to loop in the statistic next, ask all students in the sample how many ounces of water they drink in a typical day. So this is going to be a really interesting study. There's probably a lot of red flags you're already thinking about. But for the moment, let's think about just the dichotomy, population versus sample. Population is the complete set of people or things being studied. And when we mean complete set, the big red flag, the key word there is when we said all. When you're doing problems in, say, MyLab, a lot of them are multiple choice, so it's not as hard as they seem, but if you're getting a problem wrong, it's probably because just the word all is missing when you're trying to identify a population. That's the massive and major key word. We're talking about everybody or all ISU students. A sample is a subset of the population. What we mean by subset, that's a technical math term already. All we mean is the sample came from the population in the very first place. So if we have a sample of 50 from this population, they have to all be ISU students. Maybe some of them could be potentially, I don't know if that's possible, dual enrolled, I was going to say, in a different campus. I don't know if that's completely possible, but when we say we have a sample of 50, we're immediately implying, whether we said it or not on paper, because it's a subset of the population, they have to also be ISU students registered for spring 2026. We can't have a single student that's not registered, that was only registered for ISU in spring 2025, for example. It has to fit the population exactly. It's just a selection from them. Well, that's population versus sample so far. Next, we're going to take a look into parameters versus statistics, with this overall example still in mind, just to see how the definitions track through before we take on the examples below. Any last questions with the dichotomy so far, population versus sample? Okay. Here is the next level of the dichotomy. There's population versus sample, and there's also population parameters versus sample statistics. Statistics thought of as in this definition above now when we say it. So when we say population parameters, we are saying they are specific numbers of interest that describe certain characteristics of the population. So any number that describes a population, in other words, we call a population parameter, or sometimes just parameter for short. Well, we're going to figure out what the parameter is based off what the research question is all about, as defined here below the sample of 50 ISU students. Well, let's turn to the next thing, sample statistics. Much like parameters, they're also numbers describing characteristics of the sample now, found by consolidating, summarizing, computing raw data in some kind of way, collected from the sample. So that's the dichotomy so far. A parameter describes a population, whereas a statistic describes just the sample, say of 50 ISU students. Well, we have a research question as suggested. We're asking all students in the sample, how many ounces of water do they drink in a typical day? Now, I have to say, this study is probably going to run into a lot of issues because this is a variable, how many ounces they drink in a day. But I bet you're going to interview 50 students, and a lot of them are going to say, I have no clue. You're going to probably ask them to, well, just guess, estimate. Maybe you'll have a prop of like a 44-ounce cup and ask them how many of those do you think you drink in a day? But this data is going to be kind of interesting. It might not be fully reliable. And depending on how you ask this question, how much importance you put on drinking water per day, you might accidentally bias someone into saying more than they really drink. And again, they might have no clue how much they drink on a typical day. I certainly have no idea. But nonetheless, if you did the study and you have 50 pieces of information, you can calculate something. You could calculate something called the sample mean. When we say the word mean, it's not my favorite word in statistics. What we really mean is average. So if we had 50 students, let's just imagine for short, 3 students, and they told us, well, I drink 79.2 ounces. That's amazing. I don't know how they know it to the nearest tenth. Let's assume that's what they said. Another student says, well, on a typical day, I think I drink 24 ounces. Sounds like dehydrated. And maybe another one is maybe an athlete and just has to stay hydrated. And they say they drink 192.5 ounces. And maybe they have a measuring cup, so they really know, the rare student that actually knows how much they drink per day. We would add them all together, divide by the number of students, and that would be the average or the sample mean, number of ounces of water per day. So we have 50 students, we would have 50 different things all added up, divided by 50, and we would calculate that mean directly. That's a number we would know, but the unknown is the parameter. Any questions so far, just looking at the statistic side?
I just want to make sure I understand. So the sample statistics it would be the ounces of water. Is that what you're saying?
It would be the average ounces of water
Average.
among all 50 students in the sample. Let's actually write that out.
Okay.
Sample mean, number of ounces of water per day among all 50 students in the sample. Thanks for asking for the clarification on that. I think that's an important extra statement to write in, just to be specific. Does that make sense with that question so far?
Yes.
Awesome. Thanks for asking about that. Now, here's the thing that's interesting in statistics. This value is known. The original data might be unreliable. People just aren't sure how much they drink on a typical day. And what do we even mean by typical day is another question in this study. But if we have 50 different values, 50 different student responses, we'll calculate this average. We know this number. But you know what we don't know is the parameter, because there's well over 10,000 students registered for ISU in spring 2026. We don't have the resources to ask every student and get a response how much water they drink on a typical day. So that's the unknown. The population parameter is the mean. Again, when we say the mean, the word mean, what we are saying is just ordinary average. Statistics likes this word a little bit better. So the population parameter is the mean number of ounces. Let me try to spell that better. Ounces of water per day among, here's that word again. When we talk about the parameter, we're referring to the population, which is everybody at ISU. So we need to say and really emphasize among all ISU students registered for spring 2026. Kind of ran out of space there. I wanted to squeeze in this value is unknown. The reason we took a sample is we're trying to estimate this parameter, but we have no clue what it is. Whatever the statistic comes out as, the average or the mean number of ounces of water per day in the sample, if this sample is representative of the original population, maybe it's a random sample selected carefully, whatever the statistic comes out as, will be an approximation of the unknown, the population parameter in the very first place. So it's kind of messy. It's jumping back and forth, population versus sample, in a lot of different ways. But this is a typical kind of scenario, bringing together all these definitions. And when we come back on Wednesday, we'll do it again with a few more examples to see how all this goes, to really internalize all this stuff. Sorry, it looks like I ran over our last minute. Any last questions at all, folks, before we call it a night? Okay, well, have a great night, folks. We'll refresh all this terminology because it is quite a lot, and then move forward in Unit 5A on Wednesday's class. Take care.
Thank you. I may ask more questions just because I took statistics 30 years ago and had to drop it.
Good.
I got out of control really quickly. So I just want to make sure I keep it straight in my head. I appreciate it.
You bet. Thanks for the questions. I think everyone else appreciates it as well. Statistics is one of those things that it gets very messy. So keep those questions coming. I'll be very happy to help out.
Great. Thank you.
You bet.